All right, buckle up, everyone, because today we're taking a deep dive into a realm of science that's so mind-boggling, it makes the microscopic world look downright spacious.
We're talking about measurements so small, they make the width of an atom look gigantic.
We're talking about LIGO, the Laser Interferometer Gravitational Wave Observatory.
And trust me, the science behind it is every bit as incredible as the name suggests.
Before we get into the nitty-gritty of LIGO, let's remind everyone what we're actually trying to detect here: gravitational waves.
Right, because these aren't your everyday waves like the ones you see at the beach.
Not at all. We're talking about ripples in the very fabric of space-time itself.
Imagine the most extreme events the universe has to offer. Stars exploding, black holes smashing into each other. Events that release unimaginable amounts of energy.
Those events are so powerful, they actually create ripples in space-time. It's like the universe's own drum solo.
A very, very faint drum solo by the time those ripples reach us here on Earth.
Yeah.
Which begs the question, how in the world do you even begin to detect something so subtle?
That's the million-dollar question, especially when the changes we're talking about are smaller than, well, pretty much anything we can normally comprehend.
It's a monumental challenge that requires some seriously ingenious engineering. But at its heart, LIGO relies on a deceptively simple principle, the way light waves interfere with each other.
Okay, so light waves and interference patterns, this is where things start to get really interesting. Can you walk us through it?
Picture this. A laser beam gets split in two and sent down two long tunnels, each stretching for kilometers.
Kilometers. Now, that's what I call a long-distance call. And just to be clear, we're not talking about one of these setups.
You're absolutely right. LIGO actually has three of these detectors. Two of them are in Hanford, Washington, and the third one is all the way over in Livingston, Louisiana.
So they're spread out across the entire United States. That seems like overkill.
Not at all. Having multiple detectors is crucial for a couple of reasons. First, it helps to make sure that a signal is actually a gravitational wave and not just some local disturbance like a truck driving by.
That makes sense. You wouldn't want to mistake a cosmic symphony for a traffic jam.
Exactly. And second, having detectors in different locations lets them pinpoint where in the universe a gravitational wave is coming from. It's like having a cosmic GPS system.
A cosmic GPS system. I love it. Okay, back to those kilometers-long tunnels. They're arranged in an L shape, right? But how does that help us measure these tiny, tiny distortions in space-time?
It all boils down to how light behaves. You see, light travels in waves, and just like waves in the ocean can interact with each other, so can light waves.
Okay, I remember learning about this in physics class. It's all about constructive and destructive interference, right?
You got it. When two sets of light waves meet, they can either amplify each other, creating a brighter signal, or they can cancel each other out, leading to darkness.
Right. And this interaction, this adding or subtracting of light waves, that's what we call interference. But I'm still trying to wrap my head around how this helps us detect something as subtle as a gravitational wave.
Well, imagine the two tunnels of the LIGO detector as racetracks for these light waves.
Racetracks for light. I like where this is going.
A single laser beam is split, with each half sent down one of the arms of the L. At the end of each tunnel, a mirror reflects the light back to where it started.
And these aren't just any mirrors, right? They're incredibly precise.
Oh, absolutely. We're talking mirrors polished to a degree that's almost unimaginable, so smooth that any imperfections are measured in fractions of the wavelength of light.
Okay, so we have these incredibly precise mirrors at the ends of our light racetracks. What happens when a gravitational wave passes through?
That's where things get really mind-boggling. You see, a passing gravitational wave, even when originating from a distant galaxy, actually warps the fabric of space-time ever so slightly.
So it's like the gravitational wave is stretching and squeezing those kilometers-long tunnels, even if it's just by a tiny, tiny amount.
Exactly. And because the amount of stretching or squeezing is different for each arm of the L, the light traveling through each arm is affected differently. When the two light beams recombine, their interference pattern changes.
Wait, so you're telling me that this wave, something that could have come from a black hole collision millions of light years away, is actually changing the very fabric of space here on Earth, and this instrument can detect that?
In a nutshell, yes. By analyzing how that interference pattern changes, scientists can measure the incredibly tiny effects of a passing gravitational wave.
It's absolutely incredible, but we're still talking about detecting changes smaller than the width of an atom. How do they make sure everything is aligned well enough to pick up something that subtle? Any tiny vibration, even someone sneezing a mile away, could throw the whole thing off.
You're absolutely right, which is why LIGO is an engineering marvel, even beyond those incredible mirrors. We'll delve into those incredible feats of engineering right after the break.
So let's talk about those engineering challenges you alluded to before the break. It's already hard enough to picture these mind-bogglingly tiny measurements, let alone imagine actually making them.
You're telling me. Remember those ultra-precise mirrors we talked about?
The ones polished to within a fraction of the wavelength of light? Yeah, I remember.
Well, those mirrors are only part of the equation. They have to be almost perfectly isolated from any kind of external vibration.
Right, because even the slightest tremor could drown out the signal of a passing gravitational wave. And we're not just talking about earthquakes here, right?
Oh no, it goes way beyond that. We're talking about everything from traffic rumbling by to ocean waves crashing on the shore miles away.
Even the wind rustling through the trees.
Exactly. Any one of those things, and more, can create seismic noise that messes up those delicate measurements.
So how do they even begin to address that? Do they build these detectors in some kind of underground bunker, miles beneath the Earth's surface?
Believe it or not, they've done even better than that. Remember how we were talking about LEGO's mirrors being so precise? Well, it turns out their suspension system is just as impressive.
I think I read something about that. They're not just bolted to the ground, are they?
Not even close. Each mirror is suspended like a pendulum.
Okay, I get that. Pendulums are great at staying still, even when the things around them are moving. But are we talking about a really, really long pendulum here?
Think bigger. Imagine a pendulum hanging from another pendulum, which is itself hanging from yet another pendulum. It's a whole chain of them.
Wow. That's a serious case of pendulumception going on there.
This intricate system of multi-stage pendulums acts like a kind of mechanical noise filter, effectively damping out those pesky vibrations, especially the ones that could interfere with the gravitational wave signals.
So they've managed to isolate these mirrors from the hustle and bustle of the outside world. That's pretty impressive. But they still need a way to position the mirrors with that incredible precision we talked about, right?
Yeah.
I can't even imagine what kind of technology is required for that.
Well, imagine this. They use something called a Fabry-Perot cavity to make the light signal even more sensitive to those tiny changes.
A Fabry-Perot cavity. It sounds mysterious and complicated.
It might sound complicated, but the basic idea is actually quite simple. Imagine placing another mirror at the entrance of each tunnel, essentially creating a mirrored echo chamber for the light.
Okay, so now the light isn't just bouncing back and forth once. It's trapped between these mirrors, going back and forth, hundreds, maybe thousands of times.
Precisely. And all that bouncing around has a pretty remarkable effect.
Yeah.
It effectively multiplies the length of each arm of the detector.
Wait, so they're making the light travel a much longer distance than the actual length of those tunnels? Why is that so important?
It all comes down to making those tiny, tiny changes caused by gravitational waves easier to measure. Remember our limping analogy from earlier.
Yeah, the farther you walk with a limp, the more noticeable it becomes. So by making the light travel a much longer distance, they're essentially amplifying the effect of the gravitational wave.
You got it. The longer the light travels, the more impact even the tiniest discrepancy will have on its journey, making it much easier to detect. But that's only half the battle.
There's more.
They still need a way to precisely measure those minuscule changes in the light. And that's where the Pound-Trevor-Hall technique comes into play.
Okay, here we go again. Another head-scratcher of a name. Pound-Trevor-Hall. It sounds like a law firm.
It does, doesn't it? But don't let the name intimidate you. The principle is actually quite elegant. It involves subtly modulating or wobbling the frequency of the laser light, kind of like adding a vibrato effect to a musical note.
So they're adding a little wobble to the laser beam. I'm not sure I see where this is going. What does that accomplish?
That wobble creates what we call sidebands to the main laser light. Imagine it like this. You're listening to a steady tone, and then suddenly you hear these faint tones on either side of the main one, just slightly higher and lower in pitch. Those are the sidebands.
Okay, so they have a main laser beam and then these sidebands, which are just slightly different frequencies of light tagging along. But how does that help them measure a passing gravitational wave?
Here comes a really clever part. Remember those Fabry-Perot cavities we talked about, those mirrored echo chambers? Well, the main laser frequency is carefully chosen to resonate within those cavities, meaning it bounces back and forth many, many times, building up in intensity. But the sideband frequencies, they're chosen so they don't resonate.
So the main laser light is bouncing all over the place, but the sidebands are just kind of cruising along relatively unaffected.
Exactly. And because those sidebands are so stable, they act like a reference point, a ruler that never changes. By comparing the main laser light, which is super sensitive to any change in the length of the tunnel, to these steady sidebands, they can precisely measure if the tunnels are stretching or shrinking, even by a tiny, tiny amount.
So it's like they've created this incredibly sensitive measuring stick by playing tricks with the frequency of light itself. They've thought of everything.
Well, almost everything. They also have to account for the fact that gravitational waves aren't just stretching and squeezing space in one direction, they're distorting it in much more complex ways, kind of like how a rock thrown into a pond creates ripples that spread out in all directions.
Okay, so it's not just about measuring how much longer or shorter the tunnel gets. There's more to it than that.
You're catching on quickly. It's not just about the length. They actually need to measure 4 different aspects. We call them degrees of freedom of the mirror positions.
Degrees of freedom. Okay, you're losing me a bit there.
Imagine holding a pen perfectly still. Now imagine all the tiny ways you could move that pen without changing its length.
So I could rotate it or tilt it side to side?
Exactly. You could also move it up and down, or even side to side, all without changing how long the pen actually is. And that's essentially what they're accounting for with these mirrors. Even the tiniest tilt or shift, something we might not even be able to see with our own eyes, can throw off their measurements.
Wow, I hadn't even considered that. But I guess it makes sense. If you're dealing with something as subtle as a ripple in space-time, every single atom matters.
It's true. And those incredibly tiny movements, those degrees of freedom, are constantly being monitored and adjusted for.
So they've managed to isolate the mirrors from vibrations. They've figured out how to make the light signals super sensitive. And they've even figured out how to measure the tiniest of movements in multiple directions. They've thought of everything.
Well, almost everything. We haven't talked about the heat.
Heat. Where's that coming from? Is it getting warm in here? Or is that just the mind-blowing physics we've been discussing? Heat. Okay, now you've really got me on the edge of my seat. Where's this heat coming from? I thought we were talking about lasers and mirrors, not blast furnaces.
You're right, it does sound a bit counterintuitive, but the heat is actually coming from the lasers themselves. Remember, we're talking about incredibly powerful lasers here, and all that power, well, it generates a significant amount of heat.
Okay, that makes sense. But how does that heat affect the experiment? I mean, it's not like the lasers are going to melt the mirrors, right?
Melting is thankfully not a concern, but even slight temperature variations can cause materials to expand and contract, ever so slightly.
Yeah.
Remember, in LEGO, we're talking about a level of precision where even the smallest warping of those mirrors, even something we couldn't see with the naked eye, can throw off the measurements.
So the mirrors are so sensitive that the heat from the lasers themselves is enough to cause problems. That's wild. I guess you can't just crank up the AC and call it a day, huh?
Not quite. Maintaining a perfectly stable temperature in those kilometer-long tunnels would be a whole other engineering challenge.
Yeah, I can only imagine. So what did they do? How do you even begin to solve a problem like that?
Well, as with everything else in LEGO, the solution is incredibly innovative. They basically decided to fight fire with fire.
Hold on, am I understanding this correctly? They used more lasers. Because at this point, nothing would surprise me.
You're catching on. They incorporated a system of additional lasers, very carefully calibrated CO2 lasers, to heat specific areas of the mirrors in a very precise and controlled manner.
Okay, now that's just some next-level science right there.
Yeah.
So they're using lasers to counteract the distortion caused by other lasers. Did they just invent laser-based air conditioning?
It's not quite air conditioning, but you're on the right track.
Yeah.
By shaping and aiming these CO2 laser beams just right, they can counteract the warping caused by the main, more powerful laser beams.
It's like they're performing microscopic laser surgery on their own measuring device just to make sure it's working properly. It's absolutely mind-blowing. I have to admit, after learning about all these incredible engineering feats, all these mind-bogglingly tiny measurements, I have to ask, what's the big deal? Why go through all this trouble just to detect these faint ripples in space-time?
That's a question a lot of people have, and it's a valid one. But the answer, it's as profound as it is simple. Gravitational waves, they offer us a completely new way of looking at the universe. It's like suddenly being able to hear for the first time, after a lifetime of only being able to see.
I love that analogy because until recently, all our knowledge of the universe came from light, right? From telescopes that captured different kinds of light, like visible light, radio waves, even X-rays. But gravitational waves, they're a completely different beast.
Exactly. Think about the most cataclysmic events the universe has to offer. Black holes colliding, stars exploding at the end of their lives. Those events, they release incredible amounts of energy, more energy than we can even fathom. But much of that energy, it's not emitted as light, it's emitted as gravitational waves.
So we've essentially been blind to an entire aspect of the universe, to an entire channel of information until very recently.
Exactly. Gravitational waves, they pass through objects that would stop light in its tracks, giving us a glimpse into regions of the universe that have always been shrouded in darkness.
Yeah.
And what's even more incredible is that these waves, they carry information about the objects that created them, information that light simply can't provide.
So it's not just about seeing farther into space, it's about seeing the universe in a completely new way, a way that challenges our very understanding of physics and the nature of reality itself. It's absolutely incredible. And to think all of this is made possible by measuring things smaller than an atom.
It really puts things into perspective, doesn't it? The tiniest measurements leading to the biggest discoveries.
It makes you wonder what other secrets the universe is hiding, just waiting for us to develop the tools and the ingenuity to unlock them.
That's the beauty of science. It's a never-ending quest for knowledge, a journey of constant discovery that I, for one, am thrilled to be a part of.
And as always, we're grateful to have you, our listeners, along for the ride. Until next time, keep looking up at the stars and never stop questioning the universe around us.